Imagine looking at a grid of dots, what mathematicians call lattice points, and someone draws an irregular polygon on top, snapping its corners to those intersections. To find the area of this specific shape, how would you start the calculation? One way is counting whole square units inside, then accounting for partial squares along edges. Another method is decomposition, slicing the polygon into familiar triangles and rectangles. Or use subtraction, draw a bounding box and remove the negative outside space. These three methods are reliable foundations for geometry. But as shapes grow more complex, with jagged angles and irregular dimensions, manually slicing them or subtracting their borders becomes a tedious process. This raises a question. Is there a way to solve this area problem without relying on geometric slicing and subtraction? Pick's theorem offers an alternative, finding area by counting dots using this formula. Area equals I plus b divided by 2 minus 1. I represents the interior points strictly inside the shape. B represents boundary points falling exactly on the perimeter edges. This theorem implies that the internal space of the polygon is locked in a direct, fixed relationship with the dots that define it, allowing us to swap geometric decomposition for simple counting. We can test this on a simple 4x3 rectangle, which has a known area of 12. On the grid, this shape contains 6 interior points and 14 boundary points. Plugging those numbers into the formula, we take the 6 interior dots, add half of the 14 boundary dots, and subtract 1. 6 plus 7 minus 1 equals 12. Now we can apply this to the irregular polygon from earlier. For this shape, the grid reveals 11 interior dots and 11 boundary dots. In the formula, that's 11 plus 5.5 minus 1. The result is an area of exactly 15.5. If we compared this result to the subtraction method, calculating the bounding box and removing the outer pieces, the final area would be identical. Confirming the math works is one thing, but the calculation doesn't explain the logic. To understand why these numbers align, we have to look at how these shapes interact when they're combined. The logic behind the theorem relies on a concept called additivity, the way quantities behave when we cut shapes apart and put them back together. Consider two separate triangles on a grid. Their individual areas and boundary dots are calculated independently. When pushed together to share an edge, the boundary dots on that shared line change. Now enclosed by the new, larger shape, they are accounted for as interior dots. Standard area and the Pick's formula adjust in the same proportional way when shapes merge. Because the relationship stays consistent when we join pieces, the formula holds true for any complex shape built from these simpler parts. This makes Pick's theorem an accounting system. It tracks how physical boundaries are swallowed up and converted into interior space as geometric pieces are combined. Given how quickly this formula works, should we set aside the traditional geometry toolkit? In short, no. Pick's theorem is a useful enrichment, but it isn't a required procedure for finding area on a grid. The foundational methods, composing and decomposing polygons, remain the primary way to learn the relationships between shapes, lengths, and space. The value of learning this theorem lies in mathematical literacy. A good mathematician builds the ability to choose, compare, and explain different methods, depending on the problem at hand. Pick's theorem provides a playful connection between counting and geometry. It offers a way to see a rigid grid as more than just a background, but as points directly tied to the enclosed space. The theorem offers a different perspective on a familiar task, revealing an unexpected link between the dots on a grid and the area of the shapes we draw between them.